stopped worrying about what my opponents say about my videos, and myself personally, because, well, as I said on radio,
I consider them to be the human centipede. All they do is feed shit to their followers, who in turn feed the same recycled shit to others.
I don't waste my time reading their forums as often as I used to, because, well, reading their forums is a waste of time. Nor do I intend on getting into any more back and forth heated distractions. I give my attention to serious researchers, and only serious researchers, not trolls who only want attention. My primary reason for producing this video is not to address criticism of my work. More importantly, it is to address a dangerously accepted position that has been adopted, not only by my critics, but regrettably also professionals. I am of course talking about the erroneous assumption that if something is not covered in the AP8 or AE8 models for the Van Allen radiation belts, it does not exist. In July 2014, I produced a video in which I proved mathematically that the Apollo astronauts could not have survived a flight into the Van Allen radiation belts. 2 months later in September, Robert Brannig published a review. Brannig starts by attempting to twist Van Allen's statements, trying to turn his original dire warnings into an approval for Apollo's trajectory. In response to Van Allen's statement that
the discovery is of course troubling to astronauts. Somehow the human body will have to be shielded from this radiation, even on a rapid transit through the region.
Brannig makes the bare assertion fallacy that Apollo was shielded. He then proceeds to falsely accuse me of quoting Van Allen out of context. In quoting from his December 1961 Space World article, I read out his conclusion that
a living organism cannot survive this level of radiation damage. Hence, all manned spaceflight attempts must steer clear of these two belts of radiation until adequate means of safeguarding the astronauts has been developed.
Brannig reads out the sentences preceding the statement, in which Van Allen discusses how the Vanguard 1, or rather, its solar batteries and transmitter, and similar equipment on Sputnik 3 both survived years exposed to the radiation, and then concludes,
here we see that the level of radiation damage to which Van Allen refers is the integrated radiation exposures from 2 cases that were each over 2 years in duration. This statement is clearly not applicable to the Apollo scenario, where the region was traversed in hours rather than years. As before, Dr. Van Allen reveals nothing in this quote that precludes the possibility of safely transiting the radiation belts using high-speed trajectories. And even if he were referring to very short durations, he still doesn't say it is impossible, only that means of safeguarding the astronauts must be developed.
This is like saying that it is safe to eat a cyanide pill every hour, but not safe to eat one every hour for 2 years. Although Vanguard 1 and Sputnik 3 observed this radiation over a period of 2 years, the level of radiation that Van Allen refers to is on the order of tens to hundreds of Roentgens per hour. Doses on that level would be hazardous if not fatal to humans within any short time, whereas a machine should be able to handle it regardless of whether it was exposed for years or hours. On the previous page, Van Allen specifically wrote,
radiation tolerance to electronic and other physical equipment is in general vastly greater than that of animals. Typically, accumulative doses in the order of millions of Roentgens are required to produce important effects, though the characteristics of semiconductors and critical circuits may be affected by smaller doses.
So to cause damage to most equipment, we need an accumulation of millions of Roentgens, i.e. more than 2. Using the lower end of Van Allen's max dose rate of 10 Roentgens per hour, which as you will see shortly is hazardous to humans, the accumulated dose ends up being nearly 200,000 Roentgens, far below the 2 million Roentgens that Van Allen said was enough to cause significant damage to electric and mechanical equipment. Even using the maximum of his maximum, the accumulation is just below the damage dose. Needless to say, both doses would be lethal to humans, but at the rate it was absorbed, the humans wouldn't have survived past the first day. The total 2-year accumulation would have been the least of their worries. Remember, we're talking tens to hundreds of Roentgens per hour. Although the total amount of radiation detected by Vanguard and Sputnik 3 was absorbed over 2 years, the rate at which it was absorbed would have been far too much for a human to take within an hour. And so this statement is indeed applicable to Apollo crews. Clearly, Van Allen is talking about short-term exposure. As for the final statement in the article, contrary to what Brannig says, it does indeed imply it was impossible. Keep in mind that when Van Allen wrote this article, the Apollo command module and its shielding were already under development. In fact, the boilerplate test with the actual flight hull would be made just 3 years later. Adequate ways of shielding the astronauts has either been developed or it has not yet been developed. It can't be both ways. In response to Brannig, I published both articles by Van Allen on my website and released a video highlighting the quote that disproves what Brannig claims. But again, he attempted to twist Van Allen's statements into a go for Apollo. In his March 1959 article, Van Allen wrote,
Our measurements show that the maximum radiation level as of 1958 is equivalent to between 10 and 100 Roentgens per hour, depending on the still undetermined proportion of protons to electrons. Since a human being exposed for 2 days to even 10 Roentgens would have only an even chance of survival, the radiation belts obviously present an obstacle to spaceflight. Unless some practical way can be found to shield space travelers against the effects of radiation, manned space rockets can best take off through the radiation-free zone over the poles.
Brannig claims,
Dr. Van Allen does not specify under what conditions the above computations apply. However, in his 1961 Spaceworld article, he cites comparable exposure levels in the heart of the inner and outer radiation zones behind shielding meeting
Minimum structural consideration for space vehicles,
i.e. about 1 gram per square centimeter. As we have seen, Apollo was shielded far beyond minimum structural considerations, and it did not fly through the heart of the radiation zones. As Dr. Van Allen suggests, Apollo effectively flew over the poles of the radiation belts. Although Apollo did not completely reach the radiation-free zone, it did skim along the northern and southern edges of the belt where the exposure levels are greatly reduced. Rather than this quote casting doubt on the feasibility of Apollo, Dr. Van Allen provides the solution to the problem.
and he has the goal to accuse me of quote mining. Firstly, takeoff through the radiation-free zone over the poles essentially means to launch from the polar regions. Secondly, here is the quote that Brannig refers to.
With equipment shielded in about the manner that is ordinary, minimum structural consideration for space vehicles would dictate, exposure levels of some 20 Roentgens per hour have been observed in the heart of the inner zone, and exposures of several times this magnitude in the heart of the outer zone. Consideration will now be given to space missions involving prompt escape from the Earth. With Pioneer 4 as an example, the trapping region can be traversed in about 6 hours, with some 2 hours being spent in the high-intensity region. Hence, the accumulative dosage on a trajectory of this nature would be of the order of 10 Roentgens in a lightly shielded craft, 1 gram per square centimeter. In any case, it appears wise to evade the inner zone, and this is not difficult to do so as its latitudinal and radial extent is limited. The outer zone is much more difficult to avoid. There do appear to be cones of escape over the north and south geomagnetic poles. The half angle of these outward opening cones is about 20 degrees. The detailed nature of these cones has not yet been examined by direct observations.
It is obvious that Van Allen is saying that it is easy to avoid the heart of the inner zone, but not the outer zone. Avoiding this would require launching from the polar regions with an inclination to the geomagnetic poles being less than 20 degrees, which is a trajectory of 70 degrees north of the equator. This statement by Van Allen can be correlated with a 2005 textbook by Wright, Grego, and Gronlund. On page 39, the authors explicitly state,
"The electron flux is highest near the equator and becomes negligible at a latitude of 60 degrees north or south."
This latitude is close enough to that specified by Van Allen, so the minor difference shouldn't be a major point of contention. In summary, both parties state that at an inclination beyond 60 degrees, the electron flux is negligible, which is pretty much all you really need to know. By comparison, the Apollo flights were said to depart on a 30-degree trajectory. That's not even half the required minimum angle. So much for Brannig's strawman. Furthermore, Van Allen was not the only scientist who proposed launching from the poles in order to avoid the belts. NASA planners D.B. James and H.J. Schultz proposed the exact same thing after the Starfish Prime high-altitude nuclear detonation intensified the Van Allen belts. Space historian David S.F. Portree covered this in a 2012 Wired article.
James and Schultz noted that the Van Allen belts are inclined relative to Earth's equator and do not cover its poles. If the belt became impassable, they wrote, NASA would have little choice but to launch Apollo astronauts through the Van Allen belt gaps over Earth's poles. Unfortunately, Cape Canaveral was poorly placed for polar launches because rockets launched due south or north would pass over populated areas, Cuba and Brazil to the south, and the major cities of the eastern seaboard to the north. James and Schultz wrote that a country with polar launch capability might explode nuclear weapons in space to bar a nation without such capability from launching men to the moon. They did not mention the Soviets specifically, nor did they point out that the Soviet Union, with its extensive Arctic Ocean coastline, was well placed to carry out polar launches.
You can't get more explicit and self-explanatory than that. If takeoff over the poles means to go through the thin outer edges of the belt, as Brannig suggests, why the concern about the inability to easily obtain polar orbits from Cape Canaveral, or the fear that enemy nations capable of launching from the poles may detonate a nuclear warhead over the poles and effectively block their easy path to the moon with an artificially created radiation belt? Who does Brannig think he's kidding? You have to be blind, deaf and dumb to read these three sources and not realize what they are telling you. Others have argued that Van Allen says in the same paper that a shield rated at 4 grams per square centimeter reduces the radiation in the outer belt by a factor of 500. But is that safe? In 1960, Sir Bernard Lavelle published a paper in volume 60 of the journal The Observatory. In that paper, he discusses hourly Röntgen dose rates similar to those printed by Van Allen. Sir Bernard tells us that
in the heart of the outer radiation zone, the dose is about 10 Röntgen per hour, 5,000 times greater than a human being could stand.
So much for that factor of 500 reduction. Brannig then accuses me of dishonesty when I quoted Van Allen's statement that effective shielding is beyond engineering feasibility in the near future. Quoting Brannig,
White has deceptively stripped this quote of its context. The full quote is,
The exposure level in the heart of the inner zone is about 20 Röntgens per hour within a shield of 1 gram per square centimeter of iron. Owing to the great penetrability of the high-energy protons therein, effective shielding is quite beyond engineering feasibility in the near future. Hence, the inner zone must be classified as an uninhabitable region of space as far as man is concerned.
First, we see this quote is about inner belt protons, not the outer belt electrons that White has based his argument on. Second, Apollo was shielded to many times the density thickness upon which Dr. Van Allen bases his computations. Third, Apollo did not fly through the heart of the inner zone. And fourth, Apollo didn't inhabit this region of space. It skirted by it in a matter of minutes, less than 15 minutes total for both trips. As before, White seems totally incapable of comprehending that none of these quotes by Dr. Van Allen suggest in any way that Apollo was impossible. His selective editing of the second quote goes even further, suggesting dishonesty on White's part rather than simple incompetence.
Firstly, I didn't strip this quote of its context. In fact, I have read out the full quote in previous videos.
In the 1961 issue of Space World, Dr. James Van Allen stated, "A living organism cannot survive this level of radiation damage. Hence, all manned spaceflight attempts must steer clear of these two belts of radiation until adequate means of safeguarding astronauts has been developed, and that, owing to the great penetrability of the high-energy protons therein, effective shielding is quite beyond engineering feasibility in the near future. Hence, the inner zone must be classed as an uninhabitable region of space as far as man is concerned."
Secondly, I based my argument on electrons, Van Allen based his on both electrons and protons. And thirdly, in the context of discussing space exploration, uninhabitable is simply a synonym for unsurvivable. By comparison, J.W. Keller and his research team had this to say about shielding against the Van Allen protons and secondary neutrons.
The resulting shield's thickness are quite formidable, with approximately 100 grams per square centimeter needed to reduce the total dose rate to approximately 1 Röntgen per hour. Consequently, due to the very large shielding penalty involved, the intense regions of the inner Van Allen belt will probably be a forbidden region of space for manned orbiting vehicles.
And fourthly, The highest energy protons that Van Allen mentions in his article are protons with energies up to 100 megaelectronvolts. Elsewhere on his site, Brannig claims that protons are far less penetrating than electrons. In fact, he claims that only protons with energies greater than 100 MeV can penetrate the walls on the Apollo spacecraft. We'll show later that Brannig has greatly underestimated the penetrability of protons, but let's assume that he's right, and that at the same energy, protons are much less penetrating than electrons. If that is true, and you couldn't block out the protons, you would not be able to block out the electrons. Furthermore, when Van Allen wrote that statement, the Apollo Commander module was already in development and its shielding finalized. In fact, as stated previously, the first Apollo CSM boilerplate was carried into space in 1964. I never quoted anyone out of context, and even if I did, why would I then post both articles on my website and post a video containing the links and send that video to all my friends and subscribers? A person who is deceptively quoting someone else out of context makes damn sure that no one else can see the original context and wouldn't dare share it with anyone. And yet, here are both articles on my site, which is probably the only reason why Brannig was able to find the statements that he quote-mined. Brannig can deny what Van Allen's writings implied until he is blue in the face, but he is not fooling anyone who's actually read the papers. Even the Apollo astronauts themselves know for a fact that Van Allen didn't believe they could survive the journey. Frank Borman of Apollo 8, for example, indirectly mocked Van Allen twice in his book. On page 220 of his book, he writes, "The whole Apollo program made a lot of scientists look foolish, starting with those who had pronounced the Van Allen belt an insurmountable barrier to spaceflight. I have long since refused to take the word of any scientist as gospel." And earlier on page 203, slightly less than 5 hours after liftoff, we passed through the Van Allen radiation belt and Anders transmitted our personal radiation dosimeter readings. Even in the thickest part of the belt, they showed we were receiving about the same dosage we get from a chest x-ray. So much for all the dire predictions some scientists had made about harmful, perhaps fatal exposure to that belt. So much for Brannig's denial that Van Allen ever made those dire predictions. Now granted, Borman didn't name Van Allen by name in his book. Ever the arrogant coward, he only waited until after Van Allen's death to give names.
But interestingly enough, all the scientists and Dr. Van Allen was convinced that we got fried going through his ionosphere belt. This, not the doctors were going nuts, and we wonder, as if they couldn't decide whether or not they were going to abort the mission.
But I am not interested in getting into a petty back and forth, he said this, no he said that argument. What I'm interested in is mathematics. In my previous video, I calculated the primary and secondary dose rates that one would absorb from electrons with energies of 7 MeV to 10 MeV at fluxes between 1 million particles per square centimeter per second and 2 million particles per square centimeter per second. I then recalculated for electrons with energies of 55 MeV, because according to this NASA site, the average electron energy in the outer belt is between 10 and 100 megaelectronvolts, a statement that appears verbatim on this Marble website. I contacted George Balasis, the scientist in charge at Marble, and he assured me that the statement on their website is accurate, apart from the obvious incorrect units. In the original posting of his review, Brannig did not even name my reference for electrons with energies between 10 and 100 MeV, instead calling it a dubious source that shouldn't be trusted. Only after I called him an intellectual coward for not naming them, Brannig updated his site, claiming to have received an email from Sten Odenwald, the author of the NASA article, in which he claims the site is in error and that the web page was scheduled to be deleted. That statement was made in October 2014, and yet the website is still going strong. The main thesis of Brannig's criticisms seems to be denying that high-energy electrons discussed in my calculations have such high fluxes. Apparently, the AE8 max and AE8 min data from 1976, which Brannig considers the Bible for Van Allen electron fluxes, indicates that electrons approaching 7 MeV are extremely rarefied. In fact, these models stop at 7 MeV. Brannig tries to get as much mileage as he can out of these small numbers.
white would be better served focusing on 0.1 MeV to 3 MeV electrons, which represents about 99.95% of all outer belt electrons along Apollo 11's trajectory. For all practical purposes, electrons greater or equal to 6 MeV do not exist.
Brainig later concludes his review with,
White states,
"At best, 8 grams per square centimetre will stop all electrons with energies up to only 14.7 MeV.
That statement is really all you need to know. After correcting for White's errors in his computation of the hole's areal density, we see that the 7 to 8 grams per square centimetre figure quoted by NASA is accurate. We also see that, according to credible sources, there are virtually no electrons above 14.7 MeV. In fact, the definitive source, AE8, shows nothing greater or equal to 7 MeV anywhere along the trajectory of Apollo 11. Case closed.
It is not true that there are virtually no electrons above 14.7 MeV in the Van Allen belts. In fact, during my research for a university assignment, in which I had to design a spacecraft to land on Europa, I came upon this credible source by Herbert Funston and his team at the Los Alamos National Laboratory. This paper covers the helium, oxygen, proton, and electron, or HOPE spectrometers that they supplied for NASA's Twin Radiation Belt Storm Probes mission. On the second page of their paper, we are told this:
In situ measurement of this region of the Earth's space environment presents an extraordinary challenge due to the large fluxes of penetrating radiation. In particular, substantial electron fluxes are typically observed at energies that can exceed 15 mega-electron volts in both the inner radiation belt, typically centered around 1.5 Earth radii, and outer radiation belt, typically most intense near 4 to 5 Earth radii at the Earth's magnetic equator.
Needless to say, these high-flux electrons with more than 15 mega-electron volts of energy are not covered in the AE8 data, and it was during my communication with these authors that I found out why. It has nothing to do with a government cover-up, nor does it have anything to do with a lack of these particles of that energy. Quite the opposite, in fact. I contacted Herbert Funston and asked him to quantify the fluxes of these electrons. He passed my email on to one of his co-writers and world experts, Jeffrey Reeves, who I was told would know immediately. Reeves's response was as follows.
The short answer is, we don't know for sure. Most places in the magnetosphere, there are essentially no electrons with energies greater than 1 mega-electron volt. They just don't stick around long enough. In the inner magnetosphere, they can be trapped for a long time. Trapping in the inner belt is much longer than trapping in the outer belt, so the fluxes of greater than 10 MeV electrons tend to be higher and more steady in the inner belt. How high, how steady, I'm not sure. Here's why. Number 1, you need a really large detector to measure greater than 15 MeV electrons. Large means heavy, so we typically don't fly detectors that massive. The measurements we do have are typically inferred from backgrounds in detectors that are intended for other purposes, and for which the electron response sensitivity isn't well known. Number 2, integral measurements like Van Allen's Geiger tubes can tell you the total counting rate of electrons that can trigger a response in the detector, but the sensitivity as a function of energy is not well known. It's an integral measurement, but at some point, the sensitivity falls off. For instance, when an electron passes all the way through a detector, it will only deposit part of its energy. Number 3, bremsstrahlung. Any material around the detector will produce X-rays when hit by very energetic electrons. Those X-rays will often also be measured by the detector. But now the collecting area you assume isn't the entrance to the detector, it's the whole spacecraft. It is for all of these reasons that AE8 only goes up to 7 mega-electron volts. You will have to either extrapolate the spectrum and integrate it numerically, or you will have to dig into the original literature and look into both the measurements and the caveats. I'm sorry I can't just give you the answer. For the purposes of our study, designing a detector that properly measures less than 50 keV electrons and ions in a region where greater than 15 MeV electrons are present, it was sufficient to know that they can be a problem. We didn't need to know the exact fluxes. The Van Allen probe satellites have an instrument called REPT that may provide the measurements we need, but it's still going to take a lot of work to extract the correct values given the problems I outlined above. Cheers, Jeff.
And so, there you have it. The reason the AE8 model only goes up to 7 MeV is not because of any lack of electrons at higher energies. Quite the opposite. The higher the energy of the electrons, the harder they are to measure. Brannig likes to give analogies for his readers to think about. Well, I've got one for him. Let's suppose we have a big jar of sugar and a tea strainer. The strainer represents the detectors used to obtain the data that the AE8 model is based on, the grains of sugar represent the electrons, and their grain size represent electron energy, with the smaller the grain size, the higher the energy. If we pour the sugar into the strainer, we find that a lot of millimeter-sized grains accumulate in it, while most of the finer, perhaps micron-sized grains pass right through the little holes, and so only a small number of grains contained within the strainer are micron-sized. Even though there are a lot of fine grains, we can only build our model based on what was collected in the strainer. And so the model ends up looking like a 1000-to-1 ratio between coarse sugar grains and fine sugar grains. Obviously, this model does not consider the heap of fine sugar grains that passed right through the tea strainer. Nonetheless, Brannig reads this model and concludes that, for all practical purposes, fine sugar grains do not exist. While this is just an analogy, Brannig's interpretation and use of the AE8 model is exactly as just demonstrated. It could also be argued that the AX8 also fails to take into consideration the dynamics of the Van Allen belt. For example, not only do both belts contain substantial fluxes of greater than 15 MeV electrons, they can also be over-replenished by the solar activity, and the gap between the two belts can even flood with relativistic electrons. Such activity is referred to as ejection events, and since 1991, there have been many documented occasions of such. For example, on March 24, 1991, a soft X-ray solar event created a third belt between 2 and 3 Earth radii, essentially filling the gap between the two belts. This new belt was composed of electrons with energies between 15 megaelectronvolts and 50 megaelectronvolts, which took until 1994 to decay. The exact fluxes are unknown, because the measurements made by the CREST satellite were very indirect, but the instruments registered peaks close to 1 million counts per second. By comparison, the maximum count rates that James Van Allen had detected by 1958 were 25,000 counts per second, which he said were equivalent to some 40,000 particles per square centimeter per second. In covering this event, J.B. Blake et al. 1992 reported bluntly,
"The inescapable conclusion is that essentially, all the electrons just injected had energies greater than 15 mega-electron volts."
Their paper concluded with,
The event has engineering implications as well. A heavily shielded satellite in the region of the injection would suffer a radiation dose much higher than expected. It is fortunate that present-day missions do not spend much time in this region of the Earth's magnetosphere.
They also made this blunt statement.
The injection event of March 24th was truly amazing, and the observation is unique for its location, magnitude, and energy during the 35 years of space research. However, this region has not been well patrolled since the 1960s, and it required good luck for CRRES to be on the right part of its orbit at the right time. Thus, it is difficult to conclude that the event itself was truly unique.
Not well patrolled since the 1960s. Wow, isn't that revealing? No wonder we've been handicapped with the compromised AE8 models for all these years. As to whether the CREST event was unique or common, I think it has been well established that this event was not unique, as there have been many other solar events that filled the gap between the two belts, or at least moved the hearts of the belts to where the slot region would normally be. And I hate to contradict Blake here, but it's not entirely fair to say that this region hasn't been well patrolled since the 1960s. The Soviet Union had a good idea of just how energetic, intense, and dynamic the belts truly are a full year after NASA's flawed AX8 model became biblical. In 1977, the Soviets' Cosmos 900 satellite detected a 2-day increase in electrons with energies between 15 and 30 MeV due to nothing more than an increase in the velocity of the solar wind particles interacting with the belts. Between July 18 and July 19, 1977, the solar wind increased from 550 meters per second to over 700 meters per second. It flooded the Earth's magnetosphere with electrons of energies greater than 15 MeV. While the Soviets never specified just how high these fluxes were, the Cosmos 900 detected these fluxes across both hemispheres from magnetic shell or L values of 3.5 to 10 Earth radii, corresponding to altitudes up to 57,000 kilometers. These electrons occupied the entire vicinity of the outer Van Allen belt all the way to the magnetosphere boundary. Again, I do stress that the fluxes were not reported. However, the reported count rate for greater than 15 MeV electrons peaked at L equals 5 Earth radii at nearly 2,000 counts per second. Unfortunately, I couldn't find the counts to integral flux conversion factor. No two Geiger counters are the same, and each will have its own unique conversion factor. But using Van Allen's conversion factor of 1.6, this gives us a theoretical estimated flux of 3,200 electrons per square centimeter per second. Doing the calculations for such a flux and energy, we find that 15 MeV electrons at this flux would lead to an hourly dose rate of about 0.7 rads. To put that into perspective, Concorde pilots flying polar routes, where there is minimal protection from the Earth's magnetosphere, were instructed to take evasive action should the radiation aboard exceed 100 millirems per hour, or 0.1 rad per hour. This may not sound like a lot, but it should be noted that the measurements from which this dose was derived applies to a spacecraft on an inclination of 83 degrees, over 20 degrees north or south of the latitudes applied to Van Allen's cones of escape, where the fluxes are supposed to be negligible. Even sticking with 7 MeV electrons, the AE8 would have you believe that any flux approaching 1,000 particles per square centimeter per second would be too large at that altitude and inclination, and certainly that energy. And of course, the doses only get larger the closer your latitude takes you to the equator, such as on a 30-degree trajectory. This clearly indicates the AE8 shortcomings. The Soviets published various papers on these findings in the 80s and 90s. Dare I say it, more credible sources on high flux electrons with energies greater than 14.7 MeV. Credible sources that Brannig denies exists? He's clearly either a poor researcher or a bad liar. Now, while I have not been able to definitively confirm that a third belt existed during the time of the Apollo missions, the records show that they would indeed have been eligible for one. We don't know the exact electron flux of the intensified Van Allen belt, but we have a better understanding of the solar flares associated with the Kress event. M.A. Shayekdol 1994 reported that between March 22 and March 26, 1991, the Kress event flares delivered a total 10 MeV proton fluence of 9.6 billion protons per square centimeter. They also reported the solar activity of August 1972 to be 11 billion protons per square centimeter, although I think their numbers are a little bit off. R.C. Reedy 1997 estimated a 10 MeV proton fluence of 20 billion protons per square centimeter for the August 4, 1972 flare alone. It is important to note that this flare occurred between Apollo 16 and 17, and the fluence of this flare is quite considerably larger than that of the Kress event. By any definition, the intensification it would have done to the Van Allen belt probably would have dwarfed what would later be detected by Kress. Evidence for this is indicated by the fact that both of these events had similar effects on the Earth. Under usual circumstances, the auroras are typically observed at latitudes very close to the poles. But during very strong coronal mass ejections, these auroras spread down to latitudes much closer to the equator. On March 24, 1991, just days after the Kress event, the northern lights were seen all the way from New Jersey to Alabama. These photos were taken in Kansas, and the auroras are immediately obvious. By comparison, after the August 1972 solar flares, the auroras were seen in Colorado, right next door to Kansas. The lights were also reported in Miami. It is fair to say that the August 1972 solar flares probably also flooded the belts with abundant, very high energy protons and electrons. and considering that the effects of the Kress event took until 1994 to die down, it's doubtful that the Van Allen belt would have died down to normal in time for Apollo 17.
In the case of a solar flare, that can dump a lot of high-energy electrons and protons into the magnetic field. And so it sort of feeds the belts, and they do get stronger for a while, and that's when you get a lot of northern light activity, aurora borealis, in the northern hemisphere. So actually it's kind of cool. You get a solar flare, you get a pretty light show, and you think, geez, if there are any astronauts up there right now, they could be in a little bit of trouble.
I wanted to get an idea on just how big or small we can expect a flare to be in order to get the northern lights seen across lower latitudes. So I read through the scientific literature for lists of such flares, and correlated them with newspaper reports documenting such sightings. I read through Reedy's 1977 paper, this 1991 paper by M.A. Shea and D.F. Smart, who compiled an enormous list from a large diversity of other authors, and E.E. Kovalev's 1983 article. His list was rather modest, but quite useful, as his list considers the 30 MeV proton fluences alone, and provides an estimated dose from such protons for each flare. In addition, Shea and Smart also specified whether or not these flares they listed delivered ground level effect particles, or GLE particles. J.H. Reed summed up just how dangerous these flares containing such particles are with this paragraph in his 1969 paper.
The ground level effect particles are the so-called solar cosmic rays, which have energies in excess of 1 giga-electron volts, 1,000 million electron volts. Because of this, they can penetrate the Earth's magnetic field, and their effects are detectable by neutron and meson monitors at ground level stations in the middle latitudes. The particles are mainly protons with some alpha particles and a small proportion of heavier elements. The Sun-Earth travel time is less than an hour. It is these high-energy particles which are the main hazard to both space and supersonic flight. They are relatively rare, and since the first was detected in 1942, we have records of 16 events.
Shayek-Dole 1994 reported that the August 1972 solar flare was a ground-level event, while the Kress flare was not. Whether a flare will produce a ground-level detection apparently depends on the peak flux amplitude of relativistic protons. I compiled my findings in this separate table. Let's address the two famous examples. The legendary solar flare of July 14, 1959 had a 10 MeV fluence of 7.5 billion protons per square centimeter, and caused the northern lights to be seen in Baltimore. Another massive flare on November 12, 1960, with a proton fluence of only 4 billion protons per square centimeter, caused the northern lights to be seen in Miami. Kovalev reported that both of these flares would have delivered 670 rem for their 30 MeV protons. I did some calculations and arrived at similar results, which I shall explain later in the video. Of particular interest, much like the Kress event and August 1972 solar activity, both of these flares created a spectacular light show from Washington all the way down to Florida. And yet, their 10 MeV proton fluence is about 20 to 60% lower than that of the Kress event. The absolute smallest flare that I could find that was capable of creating the northern lights at such low latitudes was on September 27, 1969. It caused the northern lights to be seen in New Jersey. This flare had a 10 MeV proton fluence of 18 million protons per square centimeter. Both the 1959 and 1960 flares were ground-level events, while this considerably smaller 1969 flare was not. From this we can conclude that for a solar flare to cause the auroras to be seen across low-latitude parts of America and potentially wreak havoc on the Van Allen belts, the 10 MeV proton fluence needs to be between 18 million and 20 billion protons per square centimeter. Correlating these lists and newspaper archives, I learned that many of the Apollo missions had such massive flares preceding them. A solar flare that caused the northern lights to be seen in Washington and had a 10 MeV proton fluence of 540 million protons popped up on May 27, 1967, 18 months prior to Apollo 8. Two more flares occurred within 33 days preceding Apollo 8's liftoff. The first on November 18, 1968, delivered 1 billion 10 MeV protons per square centimeter, or nearly twice that of the May 1967 flare, and according to Shea and Smart, it caused ground-level effects. The other flare, with a fluence of 240 million protons, popped up on December 6, 1968, just 15 days before Apollo 8. Apollo 10 was preceded by two massive solar flares, one on March 21, 1969, some 2 months prior to liftoff, and another on May 13, 1969, just 5 days prior to launch. Unfortunately, I could not find the proton fluences for either of these flares, but the first had remarkably similar effects to the CRESS and August 1972 events. It caused the northern lights to be seen as far as Texas. The second flare caused them to be seen in New York and Chicago.
Did you get a chance to get that radiation survey meter out? Yeah, I did, Charlie, and I read 0 on every scale. Okay.
Apollo 12 was preceded by a massive solar flare on November 2, 1969, with a proton fluence of 750 million protons per square centimeter. Apollo 13 had not one but two massive flares preceding it, one on March 29, 1970, which delivered 94 million 10 MeV protons per square centimeter, and an earlier flare on March 23rd. I could not ascertain its 10 MeV proton fluence, but Kovalev reported its proportions of 30 MeV protons to be 16 million protons per square centimeter, about a third more than its successor. The runner-up to the Apollo 17 would have to be Apollo 14, which was preceded by 8 days by a flare with 1.5 billion 10 MeV protons per square centimeter, or about 5/30ths of the CRESS event. And yes, like the August 1972 flares, it too caused ground-level effects. I'd be surprised if these flares didn't create a third radiation belt, or at least intensify the usual Van Allen fluxes. And let's not forget the major solar flares that actually happened during the Apollo missions. In previous videos, I showed that NOAA's comprehensive flare index for major flares documents that 30 of the 1,400 solar flares during the Apollo missions were major flares. Bottom line, contrary to what Brannig says, there are indeed substantial fluxes of electrons with energies greater than 15 MeV. There is no reason to believe that the Apollo astronauts could have survived their journey to the moon. However, this does put both parties in an awkward position. Without definitive fluxes for the 15 MeV electrons, it's going to be difficult to show exactly how much radiation a person would have absorbed. Any large flux of 15 MeV electrons would be hazardous to humans, but without an actual flux, we can't exactly say how hazardous. All the papers I've read put substantial fluxes on the order of tens of thousands to millions of particles per square centimeter per second. Van Allen, for example, considered fluxes of 40,000 particles per square centimeter per second to be an enormously high level of radiation. 15 MeV electrons at that flux would yield a dose of 9.216 rads per hour, which is close enough to the lower end of Van Allen's max dose rate of 10 to 100 roentgens per hour. But again, without actual numbers, this is only an estimate. How about we take something that Brannig knows exists, something that he tried to get as much mileage as he can out of, and then turn it against his claim? Around the time he published his spurious critique of my previous video, Brannig published a separate article in which he attempts to calculate just how much radiation the Apollo 11 astronauts would have received from protons and electrons within the Van Allen belt. He makes these estimates using, of course, the AP8 and AE8 data. He provides a spreadsheet covering the first 30 minutes from the moment of Apollo 11's alleged translunar injection burn. The leftmost portion of this table lists the coordinates. Of particular interest are the L and B over B naught values. The rightmost portion lists the AE8 max electron flux values. As Brannig himself states,
since Apollo 11 occurred near the time of solar maximum, we'll use the AE8 max and AP8 max models to obtain the integral particle fluxes.
He later summarizes the total number of particles encountered for the two trips in the belt. These totals he then uses to calculate the absorbed dose from protons and electrons. His methods are very similar to mine, just a more shortcut way of doing the calculations. Instead of calculating the doses from protons and electrons at different time intervals, he focuses on the total sum of the particles. He multiplies this total number by the mega electron volts to joules conversion factor of 1.6 by 10 to the minus 13, then multiplies that by the surface area of a human, and then multiplies that by 100 squared square centimeters. Then he divides all that by the body mass of an adult. Nice shortcut, but I prefer my methods. I prefer to do my calculations the long way, more straightforward and easier to follow. Brannig himself even thinks my methods are fine, so long as I use the full surface area of the human body and the numbers from the AX8 data. This will become important shortly. Another reason why I prefer my methods to this shortcut is because Brannig's shortcut is unrealistically conservative, and I'll explain why in just a moment. Brannig then summarizes the absorbed dose from protons and electrons in one table. He gets about 89.5 rads for the electrons and 29.78 for the protons. He also estimates that the return trip is about 2/5 of the first trip. Brannig then goes on to convert the absorbed doses to the equivalent dose, that is, multiplying the absorbed dose by the radiation weight factor, or Q factor, of the radiation in question. For electrons and X-rays, the Q factor is 1, so the absorbed dose is the same as the equivalent dose. But for protons greater than 2 MeV, the Q factor is between 2 and 5. Brannig sticks to the lower end of this Q range in his calculations, so the equivalent dose for protons is double the absorbed dose. Brannig then gets a total of about 180 rem for the two-way trip, 71 of them being from protons. Brannig then makes some ridiculous comments about an astronaut being able to survive this.
A person will experience radiation sickness with a dose of 100 to 200 rem and death with a dose of 300 plus rem. Clearly, the calculated dose is significant enough to cause serious illness, but it is below that typically regarded as causing death. We see, therefore, that even a completely exposed and unprotected astronaut, i.e. one naked and outside the spacecraft, could survive Apollo 11's trip through the Van Allen radiation belts from the radiation point of view.
This is like saying that a bullet will only kill you if you get shot in the head. A gunshot to the head would certainly result in instantaneous death, but depending on where else you got shot in the body, you will either slowly or quickly bleed to death without treatment. Likewise, getting a serious radiation sickness may not instantly kill you, but without urgent medical treatment, that illness will lead to a slow and painful death. John H. Malden writes that 200 rems might be tolerable if received over several years, not hours. 180 rems is not appreciably different from 200 rems. It's difficult to imagine astronauts tolerating 180 rems within such short time frames. There is another problem with Brannig's calculations. His shortcut only considers particles with 1 MeV of energy. Although the AX8 implies that there is less of them, some of those particles will have energies of 5 MeV, 10 MeV, 100 MeV, etc. And this additional energy will add to the overall dose. We'll show later how this is indeed the case, but for now, to demonstrate the flaw in Brannig's shortcut, let's consider an analogy that nuclear physicists like to use. Let's suppose we have a multi-story car park with a load lifting capacity of 30 tons. Let's suppose there are 28 cars parked in the building. Brannig wants to figure out how much weight is in the car park, so he multiplies the total number of cars by the average weight of 1 ton. From this he concludes that the car park is holding up 28 tons of cars, which is within the building's lifting capacity. But what if not all of those cars are 1 ton each? Let's suppose 4/7 of the cars are 1 ton each, another 2/7 are 2 tons, and the remaining 1/7 weighs 3 tons. That gives us 16 tons of 1 ton cars, another 16 tons of 2 ton cars, and 12 tons of 3 ton cars. That's a total weight of 44 tons. And even though there are less of the heavier cars, the additional weight is enough to cause the car park to collapse. But Brannig's calculations indicated the building should remain standing. Why did he go wrong? Because his method of calculating involves a uniform measure of weight, and in actuality, the weight is not uniform. Now this is just an analogy, but the flaw of Brannig's shortcut is exactly as demonstrated. His calculations assume a uniform measure of energy, but the energy is not uniform, and the higher energy particles will add to the overall dose. Now of course, these calculations apply to an astronaut outside the Apollo capsule, and this is where things start to get interesting. We've already established that 7 MeV electrons cannot penetrate further than 3.815 grams per square centimeter, so we can ignore the electrons covered in the AE8. As for protons, Breunig is adamant that any protons with energies up to 100 MeV will be stopped within the human body.
The most energetic protons, greater than 100 MeV, will pass clean through the body. These high-energy particles will deposit only a fraction of their energy in the tissue through which they pass.
He then goes on to claim that all protons of energies up to 100 MeV will also be stopped within the hull of the command module. He shows a table listing proton energy versus their penetration depth in aluminium. Supposedly, 100 MeV protons are attenuated by 9.9 grams per square centimeter. No picture credit is given for this table. The reader has no idea where Breunig got it from, what its original context was, or even its relevance to spaceflight. Nonetheless, Breunig tries to get as much mileage as he can out of this table, alleging that all protons up to 100 MeV will be stopped in the spacecraft hull, leaving the only radiation damage caused by greater than 100 MeV protons, which he claims will pass right through the astronauts and deposit little energy, thus causing insignificant damage. There's just one major problem with this explanation. The table he used is erroneous and based on outdated estimates. After further searching, I managed to track down the table that Breunig shares with us. It comes from a declassified US Navy Research Laboratory report of 1962. The 9,854 milligrams number comes from an earlier 1947 report by J.H. Smith of Cornell University. And it is worth noting that for protons with energies up to 13 MeV, Smith derived his estimates from graphs printed in a Livingston and Beth paper of 1937. Yes, 1937. 17 years before the first nuclear power station was even built, and when particle accelerators were in their infancy and typically stuck around 1 to 5 MeV. Hell, the first particle accelerator capable of accelerating protons to 8 MeV only just came out that same year. Talk about outdated material. As for energies over 13 MeV, it is clear that for everything up to 400 MeV, Smith has underestimated the attenuation of these protons, while for anything over 500 MeV, it is overestimated. Breunig has clearly either never seen this table or is neglecting to tell his readers about it because it hurts his case. The most obvious indication that this graph is outdated is his estimates for the attenuation of GeV protons, protons with energies up into the gigaelectronvolt range. All modern sources, or at least the more recent ones, propose several meters of shielding to shelter against such protons. In his 1992 book, John Malden proposed 2 meters of water to shield against 10 GeV protons. 10 years ago, Eugene Parker proposed 5 meters of water to shield against 2 GeV protons. Parker's proposed shield was thicker than Malden's because the extra thickness was needed for attenuating the secondaries. In any case, because shield thickness is areal density divided by density, this gives us 200 grams per square centimeter and 500 grams per square centimeter respectively. Smith, on the other hand, proposes 994.1 grams per square centimeter against 2 GeV protons, and 5,501 grams per square centimeter to shield against 10 GeV protons. The former is equivalent to about 10 meters of water, or twice of what Parker proposed. And the latter is equivalent to nearly 55 meters of water. 55 meters of water would certainly work, but you wouldn't need that much. A shield like that would be equivalent to 5.5 Earth atmospheres. As for the validity of this 9.9 grams per square centimeter figure for 100 megaelectronvolt protons, afraid not, Breunig. An excellent resource for radiation damage during spaceflight is the 1963 book Astronautical Engineering and Science. This book was written by various scientists from the Marshall Space Flight Center in honor of Wernher von Braun's 50th birthday. Chapter 14, entitled Problems in Radiation Shielding of Space Vehicles, was written by J.W. Keller and his team of scientists, each of whom specialized one way or another in shielding against radiation encountered in space, nuclear reactors, and so forth. On page 253 of this book, they provide a simple chart plotting the range of protons in various materials against the energy of said protons. It is important to note that Brannig must have seen this chart, or at least knows it exists. Ralph Rene discussed this very chart in his own book, NASA Mooned America, which Brannig has obviously read. He refers to passages from it a few times in his site. Why do you suppose Brannig neglected to mention this chart? Well, lo and behold, it reveals that 8 grams per square centimetre of aluminium or copper being similar in density to stainless steel, would only attenuate protons with energies of about 8 megaelectronvolts. Therefore, we can conclude that protons between 8 MeV and 100 MeV will pass right through the spacecraft and bury themselves in the astronauts' bodies. Using the AP8 max data and the coordinates Brannig supplied, I decided to see how much of a radiation dose the astronauts would have received. Because of the problems with the AP8 models, we already know that the results will be underestimated. But even so, the results are quite revealing. Keep in mind that NASA claims the Apollo 11 crew only received a skin dose of 0.18 rad. All my experiences have shown that the body dose will be about 6 to 10% of the skin dose. By comparison, NOAA's J.A. McKinnon calculated that an astronaut inside the Apollo Commander module during the August 1972 high solar flare activity would have accumulated a skin dose of 358 rems, and a body dose of 33.9 rems, or about 9.5% of the skin dose. Looking at Brannig's spreadsheet, we see that the electron radiation begins at 6 minutes after TLI. For 8 MeV protons at L equals 1.5 and B over B naught equals 2.5, the flux is about 500 protons per square centimeter per second. First we convert to protons per square meter per hour, then we multiply it by the surface area of a human to get the hourly proton hit rate. Then we multiply that hit rate by the energy of each proton. Then we convert to joules. Now at this step there are two ways to go. To calculate the body dose, we divide by the entire body mass of a human. To find the skin dose, the radiation absorbed by the skin, we divide by the mass of the skin. Now the mass of the human body averages 75 kilograms. If you could take off your skin, it would have a mass of about 4.5 kilograms. After converting to grays, we convert to rem. And because we are only interested in the first minute, we divide that by 60. And so for 8 MeV protons in the first minute of transit, we get 0.017 rad for the skin and 0.001 rad for the body. That covers the 8 MeV protons for the first minute. I then repeated these calculations for the sets of protons all the way up to 100 MeV, and then listed the results in these tables. I started by measuring the doses at 5 MeV intervals, and then made tables for the protons between these intervals. A quick look at this table shows that the proton peak is within the 7th minute of transit. It also shows, at least for the first few minutes, that although the proton flux is inversely proportional to proton energy, what the higher energy protons lack in intensity, they compensate for with the energy they deliver. The doses progressively get higher and higher before the fluxes finally become too low and the doses begin to drop with them. Beyond the 7th minute of transit, the radiation diminishes slowly before finally disappearing after the 20th minute of transit. I added all these doses up and got a total of about 35 rad for the skin and 2.6 for the body. And remembering that Brannig said that the return trip is 2/5 of the first trip, this gives us a total absorbed dose of 49 rad and 3.7 rad respectively. And we still need to multiply by the proton Q factor to convert this to the equivalent dose. And so the total equivalent skin and body doses ends up being 98 and 7.3 rad respectively. And remember, this is using the AP8 max, which Brannig regards as the Bible of Van Allen fluxes. Remember too that J.W. Keller et al. Explicitly state that 8 grams per square centimeter will only stop protons with energies up to 8 MeV, and Brandy confidently assures us that the human body will stop all protons with energies up to 100 MeV. This means, according to Brandig's precious AP8, the Apollo 11 astronauts should have absorbed a skin dose over 544 times higher than what has been attributed to them by NASA. Additionally, 7.3 rad is about equivalent to 8.3 Röntgen, which is close to the lower end of Van Allen's hourly max dose rate. But I'm afraid it only gets worse than that, because remember, the AP8 is grossly compromised and underestimated. The AX8 has since been replaced by the AX9 model. While it too is compromised, the AX9 takes into consideration some of the dynamics of the radiation belt and is considered an improvement. L. Dietrich Tenko et al. 2014, for example, reported
Comparison between the AE8 AP8 and the AE9 AP9 models was conducted for all selected orbits. Results demonstrated that differences range from -70% to +170% depending on orbit geometry.
NASA's Christian Pavwar also reported,
at low altitude, less than 1,000 kilometers, actual measurements of the trapped protons fluxes are 60 to 500% higher than those predicted in the AP8 models.
Pavwar went on to provide this diagram pitching the estimated AP8 fluxes for a 690 km altitude, 29 degree inclination orbit against the SL, Houston and KA phases model for the Van Allen belt, which took averages of proton flux measurements made between 1986 and 1996. As Pavwar states in his paper,
we can see that the AP8 model underestimates the proton flux by at least a factor of 3 for this orbit. One may want to use this model in order to apply correction factors on the AP8 model.
Evidently, Brandig applied no correction factors to his calculations. He just took the AP8 as gospel and blindly assumed that it must be true. While this correction factor of 3 applies to a 690 km altitude, the inclination is close enough to that of Apollo's outward trajectory. Therefore, if we multiplied my calculated doses by the correction factor of 3, we get approximately 294 rad for the skin and 22 rads for the body. Now we are well within Van Allen's estimated max dose rate. And to put the skin dose into perspective, 200 rad is enough to cause transient skin erythema, and around 300 rads is when you start to lose hair. But again, I'm afraid it only gets worse. So far, I have only assumed, as Brandig did, that all protons greater than 100 MeV will pass clean through the body and deposit little energy. Brandig is adamant that any radiation, proton or electron, with enough energy to pass through the spacecraft will also pass through the human body. He states this repeatedly in both his Van Allen belt article and his critique of my previous video.
White calculates the penetration depth of a 55 MeV electron and concludes that it will go right through the spacecraft. Of course, this also means it will go right through an astronaut. In this case, a high-energy electron would retain most of its energy and deposit very little into the astronaut. Nonetheless, White performs this computation as if 100% of the electron's energy is absorbed into the astronaut's body.
In an online forum, Brandig went so far as to claim that a human being has an areal density of 8.8 grams per square centimeter, which is similar to what he attributes to the Apollo hull. The math he provides to try and substantiate this is laughable. The mass over area formula that he uses cannot be applied to the human body. This formula would only be appropriate if we were considering the areal density of a sphere or some other shape of uniform thickness. Because the human body is not uniformly thick, we need to use the density multiplied by thickness formula. The average density of a human is about 0.985 grams per cubic centimeter. The areal density of a human will depend on whether we're considering his height, width, or depth. From chest to back, the human body has an areal density of approximately 24 grams per square centimeter. Across his width, the body is rated at 45 grams per square centimeter. And from head to toe, it's rated at nearly 173 grams per square centimeter. And these calculations consider soft tissue alone. Bone has a density of 1.9 grams per square centimeter, and so any bones encountered along these paths will elevate the total areal density. In the case of electrons, the body depth will attenuate 44 MeV electrons, the width will attenuate 83 MeV electrons, and the height will attenuate 317 MeV electrons. Clearly, the human body is adequate to attenuate a substantial number of 15 MeV electrons in the Van Allen belt, and in most cases will certainly attenuate 55 MeV electrons. As for protons, Agosto et al. 1996 experimented the attenuation of 100 to 400 MeV protons by accelerating them towards iron and simulated soft tissue targets. This table summarizes the results of those experiments. You can clearly see that in the soft tissue target, the range for 100 MeV protons is approximately 7.6 centimeters, 15.5 centimeters for 150 MeV protons, 25.5 centimeters for 200 MeV protons, 37.4 centimeters for 250 MeV protons, and a whopping 81 centimeters for 400 MeV protons. Clearly, especially in the case of 100 to 200 MeV protons, the human body is more than adequate to attenuate these particles. Even the 250 MeV protons will be stopped within the body if they strike at the sides or straight down the height, and the 400 MeV protons will be stopped if they strike down the height. The only way the highest energy protons will pass straight through the body is if they struck the astronaut at the front or sides. So, no! Not all protons greater than 100 MeV will pass clean through the body. Sorry Braenig, but you're wrong again. This time you're embarrassingly wrong, because if high energy protons and electrons passed clean through the human body and deposited little energy, then actual atomic scientists working around nuclear reactors or particle accelerators certainly wouldn't go through all the trouble of putting thick blocks of concrete between them and the particles with energies all the way up into the giga-electron volt range.
Today, there are three main types of treatment to fight cancer: surgery, chemotherapy, and radiotherapy. Unlike traditional radiotherapy that uses photons to irradiate and kill tumor cells, proton therapy is an advanced form of treatment using protons. These particles give proton therapy its many advantages. Proton therapy's greatest advantage over conventional radiation therapy is its accuracy and its ability to spare healthy tissues. Conventional X-rays are made of photons that pass through the body and deposit considerable energy before and after the tumor. Protons, however, have a particular physical property called the Bragg peak. They're able to deposit less energy on their way to the tumor and do not affect tissues beyond it. This property allows to confine the radiation dose to the tumor and radically decreases the risk of injury to surrounding healthy tissues.
The ability for greater than 100 MeV protons to pass clean through the human body should come as a gigantic shock to medical practitioners who specialize in proton computed tomography and cancer patients who receive such treatment. As J.Z. Liang and his team of surgeons tell us,
the protons used for PCT must have sufficient energy to penetrate the body to be imaged. According to the NIST P-STAR database, the path depth or range in a continuous slowing down approximation of 200 MeV protons in a tissue-equivalent plastic is 25.8 centimeters, which is sufficient to penetrate an adult human skull. Nominal width 20 centimeters in anterior-posterior direction. For 250 MeV protons, the range is 37.7 centimeters, sufficient to penetrate an adult trunk. Nominal width of 34 centimeters, excluding arms.
now that we are all agreed that the human body can and will attenuate protons with energies up to 250 MeV, and the Apollo spacecraft will only attenuate protons with energies up to 8 MeV, this leads to the inescapable conclusion that an Apollo astronaut traveling through the Van Allen belt would be vulnerable to such protons. And hence, we can add the doses from such protons to the previous totals and see how big of a dose they would amount to. I repeated my calculations for all the protons with energies between 101 and 250 MeV, and added those to my previous results. I then multiplied them by the Q factor for protons of 2, and then multiplied the resulting equivalent doses by the correction factor of 3. And so we see that for protons with energies between 8 and 250 MeV, the skin dose on the outward trip is approximately 461 rads, and the body dose is 28.35 rads. The total dose from both trips ends up being approximately 645.5 rads for the skin and 39.7 rads for the body. Now for protons of energies greater than 250 megaelectronvolts, we need to be a little conservative. The 250 MeV protons will only be absorbed if they strike the human body down the sides or the vertical axis, and the 400 MeV protons will only be absorbed along his vertical axis. Anywhere else and they would pass straight through. So we'll consider the protons striking the astronaut from directly above. A human is about 9.5 inches from back to chest and 18 inches from shoulder to shoulder. This gives us a surface area of about 171 square inches, or 0.11 square meters. Now of course the human will be in a seated position when passing through the Van Allen belt, so we can ignore the mass of the legs. The legs have a mass of 10% of the rest of the body. Subtracting this gives us 60 kilograms. So we'll take these new values of mass and surface area and plug them into the formula. Right off the bat, I only calculated the body dose in this case because I am not sure what the mass of the uppermost part of the skin is. But we can estimate the skin dose once we have the total body dose of 251 to 400 MeV protons. Looking at these tables, it is immediately obvious that the resulting doses from each integral flux is exceedingly low, due to the rarity of these higher energy protons. Nonetheless, every little bit adds up. I added all these results up and then estimated the skin dose by dividing the body dose by 6 and then multiplying it by 100. After adding this to the absorbed doses from 8 to 250 MeV protons, we multiply the absorbed dose by the Q factor of 2 and then multiply it by the correction factor of 3. And so we see that the corrected equivalent dose from 8 to 400 MeV protons is 463 rads for the skin and 28.49 rads for the body, with the total dose from both trips being 648.5 rads for the skin and 39.9 rads for the body. And just to put the dose from the outbound trajectory into perspective, 28.49 rad is equal to 32.49 roentgens. Even though the tables show that the reported dose rates varied, if we divide these 32.49 roentgens by the 19 minutes of transit and then multiply that by 60 minutes per hour, lo and behold, the outbound proton dose rate for the Apollo 11 crew is 102.6 roentgens per hour, or slightly higher than the maximum of Van Allen's maximum dose rate. And remember, I am using the Bible for Van Allen proton fluxes and went through all the extra effort of applying the correction factor in an attempt to account for the Bible's underestimations. Now granted, my calculated uncorrected equivalent dose of 13 rads is substantially less than Brannig's calculated unshielded dose of 71 rads. I attribute this anomaly to the fact that my calculations ignore the far more prevalent protons with energies between 1 and 7 megaelectronvolts. As we established already, only those protons would be stopped within the CSM shielding. Brannig's calculations consider all protons from 1 MeV to 400 MeV and ignores the fact that the highest energy ones will pass through the body at certain angles. In any case, I think Brannig would be hard-pressed to nitpick over my results, because even after applying the correction factor, my equivalent proton dose is more than half of what he calculated. And ironically enough, had Brannig applied the correction factor to his proton equivalent dose, his total unshielded equivalent dose would have been over 300 rams. Now even though I have ignored the protons stopped in the shielding, there is also the secondary hazard. As protons collide with shielding, they knock loose neutrons from the atoms that the shielding is composed of, and these neutrons present the chief secondary hazard when dealing with proton radiation. Unfortunately, trying to estimate the flux of the secondary neutron radiation is extremely complicated and would require a new video altogether. But for now, I have a pretty good and quick way of estimating it. Returning to J.W. Keller et al. 1963's paper from Astronautical Engineering and Science, page 255 shows a graph illustrating the primary dose rate and secondary neutron dose rate in the heart of the inner Van Allen belt versus the carbon shielding in areal density. A quick look at this chart shows that for 8 grams per square centimeter of carbon, a primary dose of 10 rads per hour would yield a secondary dose of about 3 rads per hour. This means the neutron dose is equal to about 30% of the proton dose. And before anyone wants to complain that this chart is referring to the heart of the inner belt and considers a carbon shield, firstly, what I'm interested in here is the ratio between the primary and secondary doses. And secondly, you should consider my use of this ratio generous. I know that the metal on the Apollo capsule's hull is denser than carbon, but the denser the material, the higher the secondary radiation would be. If this chart considered hulls of aluminium or stainless steel, the neutron dose would be much higher. Multiplying the previously corrected equivalent proton dose by 30% and then adding that to the proton dose, we get an outbound dose of 602 rads for the skin and 37 rads for the body, equivalent to receiving approximately 133.3 roentgens per hour, and a total skin dose and body dose for both trips of 843 rads and 52 rads respectively. Now we are really close to Brannig's calculated unshielded dose of 71 rads. Amazingly, Brannig doesn't even attempt to calculate the secondary dose from neutrons. He only fleetingly mentions neutrons twice in the introduction. But again, I'm afraid it only gets worse. So far, all my calculations have used a proton Q factor of 2. As I said before, for protons greater than 2 megaelectronvolts, the Q factor ranges from 2 to 5. Since the majority of the protons in the Van Allen belt come from the Sun, I believe 5 is the appropriate Q factor to use. By direct comparison, E. Kovalev listed the 30 MeV proton fluences of various solar flares alongside the estimated doses they would deliver. Doing the calculations, we find that the doses he specified are most consistent with Q equals 5. For example, Kovalev estimates a dose of 47 rem for the January 28, 1967 flare. Plugging the proton fluence and Q factor of 5 into the calculations, I got a dose of about 45 rem. And for the legendary flare of August 4, 1972, Kovalev estimates 5300 rem, and I get a dose of 5120 rem in my calculations. These results are close enough to what Kovalev estimated, and are clearly consistent with a Q factor of 5. Interestingly, Brannig doesn't even mention that protons have a range of Q factors. He only mentions the lower end of this range as though it is the absolute one and only value of Q. I wonder why. If we sub in the Q factor of 5 and redo the calculations, we see that in the worst case scenario, the corrected skin and body proton equivalent dose ends up being over 1600 rads for the skin and 99.7 rads for the body. And after estimating the secondary neutron dose, the doses are nearly 2100 rads for the skin and 130 rads for the body. And to put that into perspective, the skin burns would have been so horrendous that the astronauts would have been 2/3 of the way to requiring emergency skin grafts. And even Brannig agrees that anything over 100 rad to the body is enough to cause serious illness. This is of course the worst case scenario. Considering the range for the proton Q factors, it is safe to say that the radiation dose that the astronauts would have received from protons and secondary neutrons is between 52 and 130 rad for the two-way trip. I repeated my calculations for each Q factor and averaged the results. I can say with 90% confidence that the average doses the astronaut should have received would have been, ironically enough, about 90 rads. But again, I'm afraid it only gets worse than that. So far, I've only considered the radiation received from the belts alone. If you recall earlier, I mentioned that there were major solar flares during the Apollo missions. In his book, Ralph Rene referred to a massive solar flare that occurred during the Apollo 16 mission.
But wouldn't you know it, I later discovered that another big flare started on April 17, 1972, when Apollo 16 was only one day out from Earth on the way to the moon. Astronauts, Young, Mattingly, and Duke should have been fried, but of course they were not.
Whilst reading through Shea and Smart's paper, I found Rene's Apollo 16 flare plus another that occurred the very next day. Unfortunately, only the proton fluence of the April 18 flare is listed. It had a 10 MeV proton fluence of 30 million protons per square centimeter, and a 30 MeV fluence of 7.8 million protons per square centimeter. Well, we've already established that the CM walls can only attenuate 8 MeV protons, and just 7.6 centimeters of soft human flesh is enough to attenuate 100 MeV protons. And contrary to what the propagandists tell you, according to J.W. Keller et al. 1963, solar flares are not directional. They reach the vicinity of the Earth in isotropic distribution because the Sun's magnetic field lines deflect them in all directions. No question about it, the Apollo 16 crew would have received these protons. Plugging these numbers into the formula and multiplying by the Q factor of 5, which was most consistent with Kovalev's estimations for proton flares, we get 6.4 rads for the 10 MeV protons and about 5 rads for the 30 MeV protons. The total dose from this one flare alone is 11.4 rads, or 13 Röntgens. That clinches it. Remember what Van Allen said about a human being exposed for 2 days to even 10 Röntgens having only an even chance of survival? Well, according to Cheyenne Smart, this particular flare reached its peak the very next day on April 19. All sources I've read put the Apollo 16 solar flares as spanning from April 17 to April 19. So if 10 Röntgens over 2 days only gives an even chance of survival, I'd hate to imagine what 13 Röntgens in 1 day will do. Even if we assume the Apollo 16 crew got lucky, and even if we ignore the extra 130 rads for the Van Allen belts, the undisputable fact is that this crew would have received a body dose of 11.4 rads from this one flare alone. The corresponding skin dose would be nearly 190 rads, over 372 times what NASA claims the Apollo 16 crew received. Case closed. The rest of Brannig's website and critique of my video is trivial garbage. For example, he jumps on the bandwagon of alleging that I don't know the difference between radiation and radioactive. You would be amazed how often I get accused of this. And it all stems from the fact that I titled my video, Moonfaker Radioactive Anomaly.
Let's start with the title. Unless Mr. White is trying to be cute by suggesting something like, this anomaly is so hot it's radioactive, he's using the wrong word. His alleged anomaly has to do with radiation and not radioactivity.
For the record, it's just a title. People who follow my videos know that I tend to use play on words when titling my documentaries. In 2008, an Apollo Lunar Surface Journal contributor by the name of Gavin Stone responded to a couple of my videos. I titled my response to him as Sticks and Stones. I did a video on the Apollo 16 jump salute, as an obvious nod to the phrase hanging 10 and the fact that what we saw on TV was a slow motion video of John Young suspended by wires. I titled the video Hanging 16. My response to NVIDIA's deception was appropriately titled NVIDIA Moons Their Customers. Even the conclusion of my GEM trilogy, which focused mainly on the Apollo 8 mission, was titled Better 8 Than Never. Nuff said. And for the record, yes, I know the difference between radiation and radioactive. Radioactive is the term applied to unstable isotopes. Unstable, meaning that they want to become stable isotopes by means of decaying on the subatomic level. Radiation is the term applied to the products of said decay. If the propagandists want to go after people who erroneously say that the Van Allen belt is radioactive, why not start with whoever narrated this Zigzag Productions documentary that they all love?
These radioactive belts form a thick ring encircling the equator, thinning out around the north and south poles.
Brannig later tries to twist statements from my previous video into something supporting his claims.
White states that even if you had the shielding rating indicated above, you would still require an inner layer of high-Z material to attenuate the Bremsstrahlung. What White is describing is, as we will see later, exactly how the command module hull was constructed.
This is a dirty lie. Normally when astronomers and spacecraft designers discuss using low-Z material to attenuate the electrons with a high-Z material to attenuate the Bremsstrahlung, the inner high-Z material they are considering is lead, not stainless steel. Referring back to the Physics of Space Security textbook, we find
a few centimeters of aluminum are sufficient to stop most electrons. However, as the electrons entering the aluminum slow down, they can generate X-rays. Thus, satellites in the most intense radiation environments may require heavy lead shielding to protect against these X-rays.
And there you have it, an outer layer of low-Z material like aluminium to stop the electrons, and an inner layer of high-Z material like lead to attenuate the subsequent X-rays. Also worth noting is the fact that the authors specifically say that a few centimeters of aluminium are sufficient to stop most electrons. A few generally means at least 3. 3 centimeters of aluminium yields an areal density of 8.1 grams per square centimeter, and would attenuate electrons with energies up to 14.86 MeV. Remember, stopping 1 MeV electrons requires 0.545 grams per square centimeter, and stopping 7 MeV electrons requires only 3.815 grams per square centimeter. If the material is aluminium, this would give a thickness of 0.2 centimeters and 1.4 centimeters respectively. Well, if most of the electrons in the outer belt had energies between 0.1 and 3 megaelectronvolts, as Brannig claimed, 3 centimeters of aluminium would be overkill. Why go through all the trouble of putting at least 3 centimeters of aluminium on the satellite with an inner layer of lead if you are not expecting to encounter large fluxes of 14 MeV electrons? Keep in mind, this credible source is intended for aerospace engineers pursuing military space applications. Brannig openly states that he agrees with the basic methods that are used for calculating the doses of electrons, but criticizes my Bremsstrahlung calculations.
White multiplies his fractions by the original electron energy to obtain the energy given up as X-rays, about 27.5 MeV. From this, he concludes that the energy of the X-rays is 27.5 MeV, which he classifies as hard X-rays. Not surprisingly, White gets it wrong again. 27.5 MeV is the total energy given up in the form of X-ray photons, i.e. the sum of the photons.
I have no idea what he is talking about. All the credible sources I've read explicitly indicate that it is 1 photon for every electron that is stopped. The opening paragraph of Haig and Nikal's textbook on Bremsstrahlung opens with this explicit statement.
The emission of a photon in the scattering of an electron in an atom is called Bremsstrahlung, breaking radiation.
The emission of a photon, not the sum of the photons. Not good enough? Okay, on 2 separate assignments that I submitted for my courses, I used this exact same formula and methodology to calculate the primary and secondary doses from electrons in Jupiter's radiation belt. Both assignments I passed, the latter of which I aced. In fact, not only did I ace the assignment, the PhD astrophysicist examiner asked me if I was interested in doing a higher research degree course someday. I think if my methods were wrong, I would have been marked down. So I'll be sticking with my university-approved methods. Thank you very much. My final point of contention with Brannig is found not in his critique of my previous video, but on his main Van Allen belt article.
Furthermore, the United States is not the only nation to have sent living creatures to the moon. In September 1968, the Soviet Union's Zond 5 became the first spacecraft to swing around the moon and return to land to Earth. The mission was planned as a precursor to a manned lunar spacecraft. It carried a biological payload of 2 Russian tortoises, wine flies, mealworms, plants, seeds, bacteria, and other living matter. The biological payload was intact, proving that it was possible to survive a lunar flight and safely return to Earth.
This would have been a good experiment had the Soviets not sent extremophiles around the moon and back. An extremophile, as the name suggests, is a life form that can thrive in environments too extreme for humans to survive in. Environments too hot, too cold, too acidic, etc. In this case, the life forms are radiation extremophiles. The death dose of insects is greater than 5,000 rads, and the death dose of bacteria is on the order of 100,000 rads. Plants are also very resistant to radiation. In the case of Zond 5, they apparently carried a spiderwort plant. Spiderworts have sometimes been referred to as a living Geiger counter. You expose it to radiation levels lethal to humans, and it doesn't die. Only its stigmas change color. In 1971, Japanese scientist Seijo Ichikawa exposed these flowers to nearly 300 roentgens of gamma rays. Guess what? They did not die. As for tortoises, they are so resistant to radiation that some scientists believe they can use the amino acids in their blood to cure radiation sickness in humans. As we are told in this UPI Science News article entitled "Tortoise Blood Fights Radiation Sickness,"
the tortoise, Tetsudo horsefieldi, enjoys a unique radiation resistance in the animal world. The lethal dose required to kill up to 50% of a population of the species is 40,000 Roentgens, compared to only 800 Roentgens needed to kill 50% of a human population. The tortoise can survive doses of tens of thousands of Roentgens.
Once again, Brannig knew this. He had to. The fact that the Zonda 5 lifeforms are all radiation extremophiles has been brought up in debate over 10 years ago by yours truly. Yet liars like Brannig and Winley continue to ignore this fact and compare apples to oranges. Let's do a quick experiment to see if there is any validity to comparing turtles with humans. It'll take too long to go through all the tables and recalculate for turtles, so for now, I will take player's privilege and use Branding's own shortcut in these calculations. We know the total number of protons allegedly encountered on Apollo 11's trajectory according to the AP8. To see how these would affect an unshielded turtle, we simply need to readjust for the surface area and mass. Looking at the actual photos that the Soviets released of the Zonda 5 turtles, the creatures appear to be small enough to fit in the scientists' hands. The average male hand size is about 19 centimeters. My hands are somewhat below average, but we'll use this number. According to this chart, an average turtle with a straight carapace or shell length of 19 centimeters has a mass of about 1.24 kilograms. Of course, its head and tail would add a little extra length. To be conservative, we'll assume a total length of 25 centimeters. Now, I don't know the surface area of a turtle, but a sphere of 25 centimeter diameter would have a surface area of about 0.19635 square meters. So we plug these values into Branding's calculations, and we get an absorbed dose of 1.99 gray, which is equal to 199 rads. And of course we must multiply this by the proton Q factor of 2, and then multiply it by the conversion factor of 3. And we get about 1200 rads from the first trip through the belts. Then of course we repeat the experiment for the return trip and add the two together, and we get a final dose of 1416.91 rads. This is equivalent to about 1600 Roentgens. Hardly enough to do any damage to a turtle, but 1600 Roentgens would indeed be lethal to humans. Even if we use the maximum Q factor for protons, the resulting two-way dose of nearly 3500 rads, or 4000 Roentgens, is still not enough to kill a turtle. How about we up the ante a little and assume that each of those protons have 8 megaelectronvolts of energy? After all, the protons need to be at least greater than 8 megaelectronvolts to penetrate the Apollo craft. And so we see that even in this exaggerated scenario, the resulting dose rate would only be on the order of 1100 rads, or some 13,000 Roentgens. Again, it's not enough to kill a turtle, but more than enough to kill a human. And that's even using the correction factor. Only by using the higher Q factors do I finally get a potentially lethal dose to turtles. But of course, this is an unrealistic scenario, because it assumes that 100% of the proton energy was absorbed by the turtles. I haven't even considered the fact that a turtle is much less bulky than a human, and thus most of the protons would have a better chance passing clean through this tiny animal than it would trying to pass clean through the more bulky human body. Clearly, the survival of the lifeforms aboard Zonda 5 cannot be cited as evidence that it is possible for humans to survive a flight to the moon. In summary, we see that Branding's attempt to imply the Apollo 11 crew could have survived a trip through the Van Allen radiation belt is based on many flawed assumptions and some outright lies. Namely, he has ignored the scientific literature that explicitly states that there is a lot more high-energy electrons than the AE8 model implies. He underestimated the path length of the high-energy protons and overestimated the attenuating abilities of the Apollo spacecraft, not to mention neglected to tell his readers about publications that he knows exists and knows dispute his spurious claims. He has ridiculously downplayed the areal density of the human body to create a false premise that most of the high-energy protons will pass clean through the body. And he has made no attempt to apply correction factors to his calculations to account for how badly the AP8 has underestimated the proton flux. In fact, he doesn't even mention how severely compromised it is. This is astonishing, considering the sheer number of scientific literature that acknowledges the AP8's shortcomings. And to top it all off, Brannig does not even have the academic honesty to accurately represent James Van Allen's statements. Instead, He adamantly denies that Van Allen ever said that it was not possible for humans to survive the radiation in the shielding available, and attempts to twist Van Allen's statements that, when taken into proper context, utterly contradict what Brannig claims. Hell, using the APA data, taking into consideration the actual attenuating abilities of the CSM and human body, and applying the appropriate correction factors, we find that the dose the Apollo astronauts would have received from protons and secondary neutrons alone would have been at least 52 rads. And the rate at which the dose would have been absorbed would have been comparable to Van Allen's max dose rate of 100 Roentgens per hour. And yet, after all this, Brannig has the gall to write this slanderous statement.
It is fair to say that no conspiracy theorist possesses the expertise to correctly solve the problem, for if he did, he would know better than to subscribe to the hoax theory.
No, Brannig, it is fair to say that no propagandist has done the math to substantiate his claim that the radiation belts would have been harmless to the Apollo astronauts, because if they did, and were honest, they would not be propagandists to begin with. Granted, you came close to working it out in your unshielded calculation, but in your desperation to downplay the numbers, you used spurious sources and ignored valid and relevant ones in an attempt to grossly exaggerate the shielding capabilities of the Apollo spacecraft and downplay the aerial density of a human to try and bolster your claim that the bulk of the radiation would not have been received by the astronauts. That is extremely dishonest. And until you stop trying to sweep valid references that contradict your claims under the rug, you will forever be branded as an intellectual coward.